Welcome to another video tutorial session on finite element procedure, which is used to solve one-dimensional structural problem. At least that's what I'm focused on now. I'm solving one-dimensional structural problem using Ansys. In my previous video, I solved this problem seen that you see on the screen. I solved it with the finite element procedure on MATLAB. And I also did an AND calculation to validate the result of that finite element procedure, which I solved using the MATLAB program. In this video tutorial, I'm going to analyze the same problem using the Ansys program. You're going to learn some new tricks which I've not talked about before in my previous video. You're going to learn about connection, how to use the connection tool in Ansys, how to connect parts in contacts. So I'm going to apply the connection functionality to solve this problem. So I'm going to start now. First, I'm going to explain the problem which we are going to solve on the Ansys program. This is the problem rather. The problem, we have steel and aluminum parts which supports a rigid bar. The rigid bar is acting as a beam, and a load of 30 kilonewton or 30,000 newton is applied at its end. At its other end, the other end is pin support and is free to rotate in such a way that when the load is applied at node 5P, the rigid bar rotates in this manner from this neutral position. So we are to solve this problem using the finite element procedure. I already solved the problem in my previous video by hand calculation and also by numerical analysis using MATLAB. So I'm going to solve this problem using Ansys. The material property and the geometric property of the steel part. The steel part is the part between node 1 and node 3. The cross-sectional area is 1,200 millimeters square. The Young modulus is 200 gigapascal or 200 times 10 to the power 3 Newton per millimeter square. The length of the part between node 1 and node 3 is 4.5 meters. For the aluminium, we have the cross-sectional area also to be 900 square. The Young modulus 70 times 10 raised to the power 3 Newton per millimeter square, and the length of the part, the aluminium part between node 2 and node 4 is 3 meters. In the question, we are told that this beam is rigid. That means under load it does not deform. It just change, it rotates or it moves, but it does not deform. So that's the meaning of rigid. A rigid bar of negligible mass. We are told to neglect the mass of the rigid bar. So we're only considering the effect of this load on this structural system. The rigid bar is 6 meters long, 2 plus 3 plus 1, 6 meters long. That is 6,000 millimeters. So I'm going to let me show you the results before I move to the Ansys program. When I solve this problem on Ansys, I got this deformation color plot. You see node 1, the node at this point, the deformation there is 0 because we have a fixed support, a pin support at that point. While the node at the rigid beam, it moves downward by 0.47341 mm. So this is the deformation at this node, 0.47341 mm. The same thing here, this node is fixed, rather we have 0 mm deformation there, but at this node moves downward 1.2334 millimeter. A node here where the point load is located moves downward by 1.6857 mm. So this is the formation color plot and the formation color plot solution for this problem. I'm going to show you how you analyze this result on Ansys. The area force color plot, the area plot, the area force, internal area force within the steel part, this part is 25,248 Newton. The unit is in Newton. While for the aluminium part, the area force is 25,901 Newton. If you want to get the stress, you just divide by the cross-sectional area. You divide this value by 1,200 because that is the cross-sectional area of the steel, and you divide this value by 900 mm square. You get the normal stress in each of the parts just by dividing by the cross-sectional area. So I'm going to move to the Ansys program now. Now we're in the Ansys work environment. So the first thing we need to do here, we need to activate our structural server, that is the static structural server. So I click on the static structural server here and I drop it at the middle of the screen. I name it one-dimensional problem. Change the name below here. You can name it anything you want to name it. One-dimensional problem. So the engineering data, we have two young modulus in our question. We have young modulus of steel and the young modulus of aluminium. So we need to define two material for steel and aluminium, which I'm going to do in the Ansys work environment under the engineering data workflow. So I will double click on the engineering data workflow to open a window where I will define the material. So I'm going to define my first material as steel. My second material, I'll call it aluminium. Aluminium. And I'm going to add, I think I didn't spell this aluminium properly, but I leave it like that. I'm going to add the isotropic elasticity property to both of them. So you click, drag and drop the isotropic elasticity on the steel, and you go to the aluminium, you do the same thing. You click, drag and drop on the aluminium. So in the steel, my steel young modulus is 200 gigapascal. The aluminium is 70 gigapascal. So I'm going to enter this value in the Ansys work environment on the steel now. So since I want to enter the value in gigapascal, I need to change the unit to gigapascal, and I'll enter 200 as the value for young modulus. Position ratio for steel, typical value is 0.3. For aluminium, change the unit to gigapascal. The young modulus is 70 gigapascal. The portion ratio for aluminium, typical value I checked on the internet, I saw is between 0.31 to 0.34, but I'm going to enter 0.34 as the portion ratio for aluminium. This portion ratio, I don't think it affects the accuracy of our results, so you should not bother about the parameter too much. So I'm going to close the engineering tab now, and we move to the next workflow. We have defined our geometric property of our material. So you need to move to the next workflow, which is the geometry workflow. So while we're on the geometry workflow, the first thing you need to do, you need to activate your line bodies by checking this box here, and you double click on the geometry workflow to open the space claim working environment. So I double click on it. The space claim working environment opens. It's opening. This might take say 30 seconds to 1 minute. So now the space claim working environment has opened. I want to sketch in in XY plane. So I'll select the XY plane by clicking this button here. I'm selecting the XY plane. I'll bring this view to plan view by clicking this button below, plan view. And the first thing I want to do, I would like to define the rigid part, which is 6 meter. 6 meter, that is 6,000 millimeter. I'm working, my unit for length is a millimeter. So this is 6 meter, which is equivalent to 6,000 millimeter. So I'm going to enter, I'm going to define the rigid part now as using the line command. I click on the line command. So from the 00 coordinates, I start my line from the 00 coordinates and I draw and I enter 6,000. I click on escape to leave the second node of the line. I want to now draw my steel part. The steel part from the question is located 2 meters, that is 2000 mm from this position. From this position, it is located 2000 millimeter along the bar, and the length of the steel part is 4.5. So in my space claim, I will hold down your shift key and move along the line and define I want to define my start node for the steel part. So I want to enter 0, my x coordinate as 2000 mm. I did rubbish. Escape, hold down the shift key from the 00 coordinate, move, okay, now 2000. Now press tab on your keyboard to move to the y coordinate, enter 0. It's very important you define it like this. If you don't define it like this, you might not enter the y coordinate properly. That's why I define it in this manner. So from here, I will draw my steel part, which is 4.5 meters. That's 4,400 mm. It's at 90 degrees. So that's what I want. So I've entered 4,500 as my length for the steel. So I've defined my steel part. I'll click on I'll press escape on my keyboard to leave that node. The aluminium part from the PowerPoint is 1 meter from node 5. This is the aluminium part. The aluminium part is 1 meter from node 5, and the length of the aluminium part is 3 meters. So I'm going to define this in the Ansys in the space clean work environment. So from this end node, hold down your shift. I will enter minus 1000 mm, that is 1 meter, as my x coordinate. Press tab on your keyboard to move to the y coordinate and enter 0 and press enter. So that is the start node of the line you want to draw now. I enter 3 meters as the length of our aluminium part. So press escape to leave command. Press escape 2 times to leave the line command. Now I've defined the parts in my model. I can leave the sketch command now by clicking on this button here. And next thing we need to do, we need to create our cross section. From the question, we have 2 cross sections, 1200 mm square for the steel and 900 mm square for the aluminium. Let's assume a square section. If we assume a square section, the cross section of aluminium will be 30 by 30, while the cross section of the steel will be the square root of 1200, which is 34 point something. I'll calculate it using a calculator. This rigid bar Because we're told that this is rigid, I'm going to give it a very big cross-sectional area. I'll give it a cross-sectional area of 500 by 500. The cross-sectional area is very big compared to the others. You can see the aluminum is 30 by 30, but the aluminum, for the rigid part, I'm going to define a cross-sectional area of 500 by 500 because we're told that this part, the horizontal part, is very rigid. So I'm going to give it a very big cross-sectional area. So going back to the space claim, go to the prepare tab. We're going to create three cross-sectional profile. So you will click on this button 3 times. One. So when you click on it, a folder opens on the left-hand side, beam profile. So one beam profile has been created. You go back to that same position, you click on it again to create another beam profile. You do it again. So 3 beam profile has been created now. Press escape to leave that command. Come to the rectangle. Right click and click on edit beam profile to change the dimension of the beam profile. Currently the B and H is 10 mm, 10 mm by 10 mm. So we need to change for steel. This is the cross-sectional area for steel. The cross-sectional area of steel is 1200. So if I use my calculator to find the square root of 1200, 1200 square root, I get 34.641 something. I copy this value, I paste it in this position. For B, I do the same thing for H. So now I've defined my cross-sectional area for steel, the square cross-sectional area. I can close this tab here, go to the structure tab, do the same thing for the second profile. This will be for aluminium. For aluminium, the cross-sectional area is 900 mm squared. The square root of 900 mm, the square root of 900 is 30. So 30 by 30. So I'll enter 30 mm here. And for the H, I'll enter 30 mm too. I will close again. For the third cross-sectional area, this is the cross-sectional area of the rigid part, which I say, because it says very stiff, I'm going to give it a very big cross-sectional area. This is not going to affect our results. Can give it any value, but I want to give it a very big cross-sectional area, say 500 mm square by 500 mm square. So enter 500 there. Do the same thing for H 500, and I will close. Now we have defined our 3 profiles. Need to apply them. How do we apply them? You go to the prepare tab under the beam panel. Let's start from steel. The cross profile for our steel is a rectangle. So I change it to a rectangle, click on create profile, and you click on the part you want to apply this rectangle profile to. So I'll click on this part. So it has been applied. I'll move to the second profile, rectangle 2, and I'll apply the profile. Rectangle 2 is the profile for the aluminium, 900 mm square, don't forget. So I'll apply it to this. The rectangle 3 is the profile for the rigid parts, the 500 by 500 mm by 500 cross section. So I'll apply it to the rigid part. Now we have apply our cross section to our 3 components. Press escape on your keyboard several times. Go to the beam folder. The first one, I will say are going to change all our parts to link type. Currently it's on beam type. You can see beam rectangle, the type is on beam. I'm going to change it to link or source type. I'll do the same thing for the second part. link or source parts, link or source type. Do the same thing for the third part, link or source. Once we have done this, we're almost done. We need to now share topology. Click on design one. Under share topology, we set at none, change it to share. So this is all we need to do on the space clean working environment. Now you can press escape on your keyboard. You can close this window, the space clean window. We are done specifying the geometry of our model. Now you see the geometry workflow is checked. That means we don't have any problem with that. Now we move to the model workflow. Double click on it. I like to turn off my internet. So the mechanical work environment is coming on. It has come on. This is the mechanical work environment where we define our mesh, boundary condition, load, and we visualize our results. So this is the workspace where we will do all that. Take some time for it to come on. It's still loading. And now the mechanical workflow has opened completely. What we need to do, we need to, on the geometric tab, let's see what we have. We have the source part. This source part is our steel. This second part is our aluminum. The third part is a rigid part. And we should notice although we didn't divide the rigid part into three parts, Ansys divided it for us into three parts because we shared topology. So the rigid part is now divided into three parts and is grouped under this source rectangle 3 geometry. The stiffness behavior for the source is currently set as flexible, which is what I want. I need to change the material assignment for the steel to what I defined. Oh, there's a problem. This is a bug in Ansys. I cannot view my material definition. There's a workaround around this. What I always do, I check this P. This is a bug in the Ansys program where you cannot apply your material to your finite element. So this has happened to me several times, but I think I found a way around it. So let me see if I can do the same thing. So what you need to do for each of the parts, since I cannot select my material, here, for each of the parts, check check this button here, make sure P is written. So for the source triangle finite element, I check the material here, you see the P button. You do the same thing for the second finite element too. You check. Do the same thing for the rigid part. I check. Now I will close the mechanical work environment. And you will see there's a change in this static structural solver. You see a 8 workflow called parameter. So you double click on it. So here you see the 3 parameters which we checked in the mechanical workflow. The first one, which is called the source triangle, that is my steel part. I want to assign steel to it. The second part, which is the aluminum part, I want to assign aluminum to it. The third part, which is source triangle 3, that is my rigid part. I can attach any material property to it, steel or aluminum, it does not matter. But let me attach steel to it because steel is stronger than aluminum. So I attach steel to it. So this is what you need to do to assign the property to each finite element. This is a workaround. Um, this is a workaround about this particular type of bug on the Ansys program. So I'll close this tab and I'll go back to my mechanical model by double-clicking on the model workflow. So the mechanical workflow is coming on again. Now the mechanical workflow environment is active. Let's check our material. Okay, still loading. Let's check our finite element material for each element. For the steel, you see the steel is assigned to it now. For the aluminium, is now aluminium. And for the rigid part, is steel. So I've assigned my material to the 3 finite elements I have in the model. This is the list of our material, but we can see that we cannot view the information of the material in this work environment. It's not supposed to be like this, so Ansys is behaving funny for this lesson. For each of them, we cannot view the property. So move to the cross section. We should have 3 cross section here because we created 3 cross section in the space working environment. The coordinate system, we have 1 coordinate system. We can choose to create a coordinate system if we want for order to suit our use, but I don't need it for this lesson. So I'm not creating a new coordinate system. Under the connection, we need to connect the rigid parts, to our aluminium and the steel using the connection tool here. So what you need to do, you need to right click on the connection, insert, manual contact region. We need to create 2 of these because we need to create 2 connections. So I will duplicate this bonded node selection, number of selection to number of selection. I'll click on it, duplicate. So I have 2 of it now. The first one is the connection that attaches the steel to the rigid part, while the second one is the connection that attaches the aluminium, this to the rigid part. So this is what we need to do. We need to specify the connection for the first part, which I'm defining as steel rigid part connection. We need to define our contact and the target element for that connection. I have an image which I want to show you to explain which is contact, which is target. I think I have it here. So the contact body is the body in which the force is applied to. The target body is the body in which the contact surface touches or is attached to. So that is the definition of contact and target. The contact body is the body where the force is applied to, while the target body is the body without contact force. This body will touch, this contact body makes connection to this target body. So this is the explanation for contact and target. So for our steel rigid body connection, our contact selection will be the rigid part because the force is applied to the rigid beam. So I'm going to select all the rigid parts and I will apply it to this contact. I will apply it here as contact body. The target body steel, I will apply on the target role. So this is the definition of connection for the steel rigid body connection. So we need to define for the aluminium rigid body too. So you go to the second connection which we created earlier. You define the contact and the target body. The contact body for these two is also the rigid part, because the rigid beam is a load. The load is applied to the rigid beam. So I'm going to select the three parts of the rigid beam, and I will apply. The target body will be the aluminum part. I will apply to target body. So this is how I define connection um, in this one-dimensional structural body. These are the two connections. This for the steel, this for the aluminum, to the rigid parts, to our rigid beam. One more thing, for the rigid, under the geometry, for the rigid elements, I would like to set the stiffness behavior from flexible to stiff beam. So we have an option to um, define if our finite element is going to deform or if it's not going to deform. So even though I didn't define a big cross section for the rigid beam, which I define as 500 by 500, even though it's 10 by 10 mm, and I define the behavior here as stiff beam, it means that no matter the load applied to that material, the material, that part that you define as stiff beam, is not going to deform. It's only going to change position due to the applied force. The body is only going to move, but it's not going to deform. So we can see the other two parts, steel and aluminum, is set as flexible, which is what I want. We have defined the connection here, and the connection definition is bonded, bonded. There are different, you should do your research on the different type of connection. We have bonded, no separation, frictionless. But the bonded connection is the type that work for this. What I know is that the bonded connection is what works for this problem on Ansys. Under the mesh, I normally use the greatest dimension in the model as my size of for my element size. So for this problem, the greatest or the largest dimension is 4.5 meters. So my element size will be 4,500 for one-dimensional problem. This is for one-dimensional problem. So go back to the mechanical view. Under the mesh, element size 4,500. The element order linear. Now we have defined the mesh. We need to define our connection. So at this node here, we have a pin support that is free to rotate, but it's fixed in the X and Y direction. So I'm going to create a displacement support at that point. It's now at that node. I'll define my X as 0 mm, my Y as 0 mm. I can also define Z as 0 mm. I think if I should define Z as 0 mm, the joint will not be able to rotate, so I'll leave it as free. So just X and Y as 0 mm. I'll create another support. I'll select this node here. I'll create another displacement support, and I'll define the X, Y, and Z as 0 mm respectively. I'll do the same thing for this node here. Create another support, displacement support X, Y, Z as 0 mm. I'm also going to define some displacement boundary condition at this support. Insert displacement boundary condition. I want the Y to be able to move in the Y direction. That node should be able to move because my deformation for the steel is along the y direction. So in the y direction it will be free, but in the x and z direction it can be set as 0. I'll do the same thing for this node. The y direction it can move because that is my the y direction is my dimension, is my degree of freedom dimension, the y direction. So I've selected this node here. I'm going to insert a new displacement support. The y will be free, the x will be 0, the z will be 0. At this node too, I'll do the same thing. Displacement support, the x will be 0, the y will be free, the z will be 0. Now I've defined all my bounding conditions for the support. We need to now insert our load at this point. At this point, we need to insert our load. In the question, the P is 30 kilonewton, 30,000 Newton. So I'm going to insert a load, a point load at that point. Insert force. It's already selected, defined by components. The force is along the y direction, 30,000 Newton. Minus 30,000 newtons, pointing downward. So this, I've defined the boundary condition for my problem now, the support and the forces. So now I can run analysis, but I don't want to do that. Let me add the solution that I want to view before I run analysis. So I click on the solution, insert deformation. I want to see the deformation in the y direction. So make sure the orientation here is changed to y. I want to see the area force in the finite element, beam result area force. I don't need to change the setting here. I want to probe the reaction at the supports, at supports. I will insert actually 5 probes to probe the reaction for this problem. Probe force reaction. So I'll create 5 of these. Let me duplicate 5 of these. 1, 2, 3, 4, 5. With the first force reaction, I want to probe the reaction at this node. So the boundary condition there is, remember, is displacement 2. I know. It's displacement 2. I don't know why it's not displaying. It's supposed to be displayed, but I know it's displacement 2 because it was the second boundary condition I defined. I think this was the third boundary condition I defined, so this should be displacement 3. So force reaction 2, I will attach displacement 3 boundary condition to it. Force reaction 3, which is this here, this point here, I will attach displacement boundary condition 4 to it. Force reaction 4, I will attach going on force reaction 4. I'm going to attach displacement boundary condition 5. Force reaction 5. I'm going to attach displacement boundary condition 6. Now I'll run the analysis. Let's see what happens. 10% complete. 10% building mathematical model. This will take some time. It is complete now. You can see my rigid beam, 500 by 500 square. Ooh! Yes. Let's start from directional deformation. Let's view this in the z direction by You need to click this Z axis. So we can play the animation to see how the body is deforming. Wow, the deformation is how I expected. But let's probe the deformation value at the node to see what the Ansys result gives us. Let me end. Go to the result tab. So click on this probe at this node, 0, this is 0, 0 deformation at that node, which is what I expect. This is minus 0.48481 mm. At this node, it is minus 1.2218. At this node, it is 0 displacement. At this node here, is minus 1.4895. I would like to compare these results with our manual calculation with our hand calculation on the PowerPoint. So for the steel part, the deformation is 0.4848. So let's check in the PowerPoint manual calculation which we did in our previous lesson. So this is the deformation for the steel is 0.4876. 4876. In the Ansys, it is 4848, which is very close. I think the result is good. As we know that the finite element is an approximate method, as we always say. For the aluminium, the deformation is 1.2218. So if we should check, we have 1.2189. 1.2189. We are getting 1.2218, which is also very good. My hand calculation, I did not calculate for this node, but I got the result in my finite element procedure on MATLAB. But my MATLAB is not open, so I'm not going to waste my time on that. And we can see the beam is deforming as I expected. It's rotating about this point here. So these are our deformation results. Let's go to our axial force results. The axial force, let's use the probe tool to determine the axial force in our steel and in our aluminium. The axial force in our steel is 25,856 Newton, while in the aluminium it is 25,657 Newton. So let's compare this result with our hand calculation. For the steel, it is 25,856. 25,856. The reaction force for the aluminium is 26 kilonewton, like 26,005. That is the axial force in the steel, R1, 26,005 Newton. And I'm getting 25,856 Newton, which is very close. For the aluminium, I'm getting 25,656 Newton. For the aluminium, the axial force acting is R3, and R3 is 25,598. 25,657 Newton. Axial force result is also very close to the hand calculation results. The force reaction for at this node, force reaction is pointing upward. And if I click on the tabular data, I see the force reaction to be 25,856 Newton. For the second node, for this point, the fixed support here is 25,657 Newton. For this, it's not displaying properly. The result at this 3 position is not displaying properly. The y axis is not giving me result on the y axis. But what is important is that we can get results at the top. First reaction at this node is 25,856 Newton, and the first reaction at this point is 25,657 Newton. So this is how we use Ansys program to solve this particular type of problem. Before I close one-dimensional analysis, I would like to solve one more problem. One more one-dimensional problem is a symmetric type of problem. I'll show you on PowerPoint. I'm not going to do a calculation on that problem because I've done that several times. I'm only going to solve the problem on Ansys. And the reason why I want to do it on Ansys is because I want to show you how to use the symmetric tool, how to reduce our model by half, or how to reduce your model by at least half to increase computation speed on your computer. So this is a symmetrical type of problem. We can see at this axis, the material part on the left is also what is on the right, and also the loading on the left is also what is on the right. So the response of this body to external force will be also the same. The internal stress and strain will be the same. The reaction values will be the same. So this type of problem can be reduced to this form. We place a pin support here. In Ansys, there is a tool we attached at this point called the symmetrical tool, which we can use to solve this type of problem. So I'm going to show you how to solve this type of problem using the symmetrical tool in Ansys in my next video. Thank you so much for taking the time to watch my video. I'm so grateful. Stay tuned for my next video on the last problem, which I'm going to solve on one-dimensional problem, which is this problem. After this problem, I'm going to move to source analysis using the Ansys program. In that section, I'm going to do different type of analysis too. I'm going to do plane analysis. I'm going to do plane truss analysis. I'm going to do 3D truss analysis. I'm going to analyze truss with inclined roller supports. I'm going to solve about 4 to 5 problems under the truss analysis using the Ansys program. So thank you so much. Stay tuned and look forward for my next video on YouTube. Have a nice day.